Okay, normal and tension forces. Normal force is a force between two objects through direct contact. It is called the normal force. Oops. Because normal is a word within mathematics to refer to a 90-degree angle. And the normal force, called the normal force because it is always at a right angle to the surface that produces it. So let's imagine you are standing on the floor. There's going to be a force acting on you due to the ground, that is the normal force. There will also be a force on the ground due to you, which is the normal force, and those two separate forces would form a third law pair. It is perpendicular to the surface, so the surface is nice and horizontal and flat, the force will be vertical. Vice versa, imagine that you are now pushing on a wall. Then you are going to experience a normal force that pushes back away from the wall, and the wall will experience a normal force that pushes into the wall due to you squeezing against it. And one last example here. The lovely inclined plane. If you are walking up a ramp, there will be a normal force that acts on you, and it will point, again, perpendicular to the surface, and you will produce a normal force on it. It's a third law pair force that is perpendicular to the surface again. It really is kind of a cool thing. If you have something that's a sphere and you come along and you try and push that sphere, if you're pushing at an angle like this, then the normal force on you will be at an angle and the normal force on it will be at an angle such that it is normal to the surface of the sphere. So depending on where you push it, it will be rotating right around, so it's always perpendicular to the surface. That's just the way normal forces work. There's no special math behind them. They're always going to be driven by other forces that are acting, and they will support you against those other forces. Basically, normal forces are there to keep you from going through material. Now, what causes a normal force? Well, I'm not going to get into much detail on this, but you can essentially think of all materials like solids as being made of a grid of atoms connected together, like masses connected together with springs. The bonds between the atoms act quite a bit spring-like. So if you imagine what happens if you come along and you try and set something on a springy surface like this. I'm going to just do a quick copy-paste. So we'll come along, we'll bring our object and we'll try and set it on it. And the final result of trying to set it on it will be that the bonds will distort a bit between the atoms. And it's that distortion of the bonds that will create the normal force. So now you can see some of the springs would tend to be pulling up on the surface, which would be pulling up on our object. So this is atoms as masses, connected by springs and bonds, distorted by the weight or the object sitting on top of it. And that ends up creating our normal force. Cool thing is, this means that the normal force is, on its deepest level, technically electromagnetic, because the bonds between atoms are very much electromagnetic, mostly electrostatic. So that's pretty neat. We don't need to know the details, but the details are cool. All right, tension force. Yeah, tension force. Second part. This one gets a little bit more involved because tension is a little bit weird. Okay, tension is also an outgrowth of electromagnetic attraction. Essentially, if you imagine that you have a rope, it's a bunch of little masses effectively connected together by springs. So when you try and pull on it, you end up stretching those springs and you end up creating a force within them. And that force gets transmitted through the rope wherever it happens to be. So it's also electromagnetic at its deepest level. But the special thing about tension, you can't push with a rope. So as a general rule, tensions should not be used to push things around, only to pull them. And then ropes redirect force. In other words, the tension. So the simplest way of thinking about this is imagine you have a couple teams of people and they are engaged in a tug of war with each other, and you've got your rope in between. They pull against it. If you inserted a scale in here, it's going to read some force F. And it turns out if you also measure the force that is being exerted by somebody on either end, the force you measure here and the force you measure there, we'll call that F1, F rope, and F2, because this is team 1 and team 2. F1 will be equal to Fr. The force inside the rope will be equal to F2. So, tension is same everywhere inside a, in quotes, massless rope. Now, of course, no rope is literally massless, but if the weight of the rope is a lot less than the tension force you're producing inside it, you can act as though the weight of the rope is zero. So as long as the weight of the rope is much less than the tension you are putting into it or have in it, we don't need to worry about it, which is nice because it would be a pain. All right. The redirection aspect of this gets kind of weird. Imagine we have the same two teams playing tug of war with each other, but this time we've got a nice frictionless bearing on the other end. So the rope goes around and comes back to the other person. I'm going to try and shift them up a bit. Yeah, that'll do. 2, and then we'll finish the rope. You might be surprised to learn that if you put the same meter here and measure your F1, F2, and then right where it's contacting here, measure the F in the rope, you'll find that every single one of these, all of them are equal. That has interesting consequences for our little bollard here, our little bearing that redirects the direction of the rope, because we would actually find that it experiences tension twice, pointing towards the people who are pulling on it. And then each of these people would experience the tension pulling them towards this bearing. So that is the creepy, weird thing about tensions. Tensions redirect forces. Tensions are always going to act to pull on things. They're not going to act to push on things. If one of the teams was actually stronger than the other, and they weren't static in this case, say team 1's weaker than team 2, so the whole thing is shifting kind of like that, the tension would still remain the same. They'd both be experiencing the same force. The bollard would still be experiencing two tensions pulling on it, or the bearing would be experiencing two tensions pulling on it. You would not ever have a situation where you have tension going this way and tension going that way as the rope is wrapped around. That does not happen. That is one of the hardest things to remember about tensions. All right, we're coming up on 10 minutes. I think I've said everything I need to say here. Pulley problems and tension problems can get tricky because of that redirection. So if you're solving a problem like this, you may end up having to kind of rewrite it. So you visualize it as though it's been linearized. You take one direction and you say, that's going to be my positive x. And then what you end up doing is wrapping everything around so that here's team 1, here's the rope, here's the bearing, here's team 2, and we see the tension pulling this group this way and that group that way, and then they have their own individual forces. So we've just kind of linearized the whole thing out, taken this and essentially curved the positive x-axis to go around this bearing. All right, that can be helpful for solving problems. I talked about it in the lecture for class as well, or I talk about it in the lecture for class as well. So you can look it up there, and we do a problem related to that, a couple problems related to that. Otherwise, that's all I have to say for now. This has gone on longer than I'd wanted. Should have split it in 2 parts, but there we go. All right, then I will see you in the next video.